welcome back, everybody, for the afternoon session. I'm very pleased to introduce Mike Ackerman.
I realized the title, I didn't change the title, so that's not the right title.
Who will speak on the top.
Very close, so this is the right title. Okay. But first of all this work is joint work with Rohan Patel and Cameron Frere. Okay, so here we're going to talk about algebraic and definable closure. So the we'll define what they are in a second, but the motivation is these are sort of abstract notions of a neighborhood in a logical structure. So the definable closure is a little more restrictive, and the algebraic closure is a wider notion of neighborhood. And they have several sort of applications in wider sort of mathematics. So one important point is that if you have trivial algebraic closure, so if your neighborhood is trivial about it inside itself for algebraic closure, the neighborhood for the definable closure is also inside. That's not a hard proof, but worth noting. But structures with this property that your sort of algebraic closure is trivial sort of come up a lot. So some of the places where they come up is we're studying sort of universal graphs between subgraphs. This notion of having trivial algebraic closure is really important. Likewise, if you're interested in measures which are exchangeable, the idea is basically you have some way of sampling a structures where if I interchange the underlying set, I don't change the distribution. Then I can construct a structure in this manner, like say the Rado graph, if and only if the structure has trivial algebraic closure in an appropriate sense. And also in sort of ergodic structures, this notion of sort of structural equivalence relations, when you're sort of looking at a structural equivalence relation over a single structure, that sort of only makes sense if the structure has trivial algebraic closure. So the point of this is that this notion comes up naturally in a bunch of different areas. Another one, as when I was talking about for Z limits, is for Z limit has trivial algebraic closure if and only if the class has something called strong amalgamation. Okay, so what is it? So let's first going to talk about first order definable closure. So the idea behind first order definable closure is I have a tuple and I want to look at all of the elements which can be pinned down precisely by a first order formula with parameters from your set. So that's what this says. So it's the smallest set such that there's some formula, and there's some tuple from my set, such that the number of realizations of that formula where those parameters is precisely one. There's only a unique realization. And further, the realization is in the sort of definable closure. Now, you'll notice that there's a lot of sort of things, a lot of sort of adornments on this. Now, there's a superscript 1 and a subscript L omega omega. And the reason for this is this particular definition is sort of a one-step definable closure, meaning that I'm looking at all the formulas, I'm looking at all the things which are definable over parameters for my set, and then I'm saying I'm good. And I'm not sort of iterating. And the L omega 1 omega means I'm looking at all first order formulas. So I'm looking at all formulas you can imagine in the first order. Now, there's generalizations of this to higher order logics, but we're going to stick to first order formulas. Now, an important point here is that if I iterate this process with all first order formulas, I get the same thing if I just do it once. So what this means is that this particular definition gives me a closure property. Now, in general, this is if I sort of change all of first order logic to subclasses of formulas, as we'll do, this is no longer the case. You have to sort of iterate the process to get the full definable closure. Okay, so let's go through some examples. So the first obvious example is if I'm in a language with function symbols. Well, then the function symbols are going to naturally define, like the images of the functions are naturally going to define something in the definable closure. If I have a tuple and I have a function that I apply to the tuple, there is only one element which realizes the statement I am equal to f of my tuple. And so everything that is sort of in the functional closure is going to be in the definable closure. And in general, this is not a bad way to think about this. Somehow, if I have a partially definable function, then I sort of throw in all the images of that partially definable function on things in the set I'm trying to take the definable closure of. All right. Another example is the natural numbers. So, natural numbers, the definable closure of the empty set is everything, because I can say I am the least element, and there's only one of those. I can then say I am the successor of the least element, and there's only one of those. And so for every natural number, there is a single formula which pins it down uniquely. And so taking the definable closure of the natural numbers gives me everything. All right, now a non-example is instead of looking at the natural numbers, suppose I look at the integers. Well, now I look at the definable closure of the empty set. It's actually nothing because there is no single way to pin down a single element without things named. So like there's automorphism, which takes any element from the integers to the other elements, where here the only sort of relations are the successor relation. And so there is no single thing that can be pinned down by a single formula. Likewise, if I name a single element, there's nothing that can be pinned down by a single formula because assuming the successor relation, you can always sort of commute the things. Okay, so that's algebraic closure. Now let's go to definable closure. Now let's go to algebraic closure. So as I said, this is a sort of more general notion, or sort of a wider notion of neighborhood. So the idea behind definable closure is if I can pin down an element uniquely by a formula, I want to throw it into my definable closure. With the algebraic closure, I don't want to just look at things I can pin down uniquely. I'm allowing myself a little bit of wiggle room. As long as I can only pin stuff down up to finitely many versions of them, then I throw it in. So that's exactly what this says. It says that, there's some first order formula where the set of realizations of that first order formula over parameters in my set is finite. And I throw in all of those realizations. And likewise, like in the case of definable closure, what we have that if I do this twice with all first order formulas, nothing changes. But once again, I have this sort of adornments because in general, we're going to want to look at this not for all first order formulas, but for sort of computable classes of formulas. And that's what happens. And there, taking that, if you want to take the full closure relation, you have to iterate this arbitrarily often, or finitely often at least. Okay, so let's look at some examples. So binary tree. This is a good example to keep in mind. If I look at the sort of the root node, there isn't anything in the definable closure because every node has other things that look exactly like it. They don't have many of them, but they have other things that look exactly like it. So the sort of two nodes level one, they're not in the definable closure because I can't identify them. But there's only finitely many things at the next level. So I can say, so saying that you are at the next level of the node is in the algebraic closure because it's not, you can't identify it precisely, but up to the finite amount of sort of wiggle room. So in this context, the algebraic closure of any point is going to be the whole tree. Okay, so another example, and one that I'm sure will surprise absolutely no one, is if I have a algebraically closed field K, and I look at some subset of that field, the algebraic closure is going to be the algebraic closure of that subset. Because the algebraic closure of the subset basically says, for every sort of collection of parameters, every solution to an equation in those parameters is thrown in. And well, there's only, given any equation, there's just sort of finitely many solutions. And so for any equation, only ever thrown in finitely much. And while I don't know the history precisely, I would imagine this is one of the sort of few reasons why it's called the algebraic closure in the definition. Okay. So, to back up. So before we go on to actually talking about these things from a computability standpoint, we want to sort of give a little bit of background notation. So first off, we're going to work in a multi-sorted structure. Now, roughly speaking, those of you who don't know, a multi-sorted structure is just like you would think of a normal structure, but every element is attached to a sort. It needs to be encoded by unary relations. But when you do, your theories have sort of weird garbage off that aren't part of any sorts. So by declaring by fiat, everything has a sort. It sort of simplifies this. Now, nothing we're doing in terms of the computability bounds really matters, or whether or not you're multi-sorted or single-sorted because of this encoding. But one of the things we're going to want to do is not just find structures that witness the computability bounds, but find structures that witness the computability bounds that are nice model theoretically, the extent to which we can. And there are a few examples where having multi-sorts makes things easier, where when you don't have the multi-sorts, you have to worry about this garbage that is a little bit annoying. So we're always going to always work in a multi-sorted structure. Notationally, the type of an element is just the collection of sorts of each of a tuple, is a collection of sorts of each of the elements. And we say, for all x, colon x just means it's x is of type x. Don't worry too much about this if you're not familiar, but those who are, that's what the notation is. All right. More relevantly for this audience is we want to sort of work with computable structures. Now we had a couple definitions, so we'll go through the ones that are used here, which is very similar to the others. So a computable language consists of a collection of sorts and a collection of relations, which are each encoded by numbers, along with a function which takes each relation and tells you what collection of sorts the argument has. In the one sort of case, this would be a function which takes the relation and tells you how many arguments it takes in. And it's a computable language if this function is computable. If the index sets are all subsets of computable subsets of the natural numbers and the function is computable. A computable structure is then one where basically I can computably define the set of A comma J, where xj is the sort of A. So I sort of can computably define each sort, and for each relation, I can computably tell you whether or not you're in that relation. So from this, you can sort of, any quantifier-free formula, you can sort of figure out a computable net. Okay. Now, a code for a structure, once again, not surprisingly, is going to consist of a computable function where the first, the output on the first input is a code for a language. The output on the second input is a code for a theory, for a model, and of that language. And we're going to use the notation L sub C, M sub C, and T sub C for the corresponding language, model, and theory that corresponds to the code we're given. Okay, we also let comp stir be the collection of all codes, all natural numbers, which are codes for substructures. Okay. So we talked about full first order algebraic and definable closure. But what we're really interested in is the formula by formula analysis. So where we're not just looking at the closure over all formulas, but we're looking at it over specific collections of formulas. So we're going to define these sets. I'll go through what each of these are now. So the first one is the collection of tuples C, which is a code for structure, a formula, and a tuple in the structure, along with K, which tells you how many realizations of that tuple you have. So from a computability point of view, if you're interested in sort of studying the algebraic closure, the definable closure, where you either have finitely many realizations or one realization, this encodes all the information you need to figure that out, at least in the one-step iteration. Now the algebraic closure, which is exactly what you think it would be, it's the collection of tuples where for some K in the natural numbers, there are exactly K many realizations. And for DCL, we likewise say that it's a collection of tuples where there is only one realization. Now, a little bit of notation here is we're going to put on the subscripts, subscript n, if we only care about Boolean combinations of sigma n formulas. So when there's subscript 0, that means we're looking at the quantifier-free formulas. And we're going to also add a superscript to basically say what code we're looking at. What's the code, the sort of model we're looking at. All right, so now one of the things about the previous sets is this is talking about the one-step iteration, meaning I have my set, and I'm looking at, for each formula, I tell you how many realizations I have over parameters of the set. Now, in general, that's not going to be enough to get a closure relation, because if I sort of iterate this process, I might get more and more new elements. So we're going to find the sort of lowercase ACL and DCL, where what's happening here is the one-step iteration is you take a set, and for every, let's say, the algebraic closure, for every formula in your distinguished collection phi, if there's only finite realizations, you throw in all those realizations into the set, and you get a larger set. And then you iterate this process until it stabilizes. And so this will actually give you the full algebraic closure as opposed to the one-step algebraic closure. And likewise, you're going to do a similar sort of thing for the definable closure. Okay, so now the main thing we're interested in is we're interested in the sort of computability theoretic content of how complicated these sets are. The capital ACL, capital DCL, which is the one-step iteration, and the lowercase, which is the full closure operations. Okay, so now we're also going to sort of, for notational purposes, just going to define ACL phi sub c as the set of finite tuples and elements A, which are in this algebraic closure of the finite tuple. Or in the DCL, which is in the finite tuple, and the A in the definable closure of the finite tuple. And this is the sort of the subset of natural numbers, or sort of computable subset we actually want to get the precise computability theoretic complexity of. Now note that as part of the subscript, we are considering a finite collection, or a countable collection of formulas, which is also computable. So we're not requiring this to be over all computable formulas, all first order formulas, but we're allowed to sort of choose a computable collection and say, I only want to look at the algebraic closure over this collection. And we'll show that you can get upper bounds for arbitrary computable collections, and the lower bounds can actually be done with really, really simple languages. Okay, so now let's look at the complexity of the algebraic closure and definable closure relations. Okay, so first thing to notice is this class of all structures, Comstern. It's a pi02 class. So this is kind of problematic for actually studying the full capital CL, capital ACL, capital DCL, because even ignoring any information about formulas, we already have a pi2 collection by just considering all of the structures that you have to be. So I can just ignore the last coordinates, just look at the first coordinates, and already is very complicated. What we want to do is instead say, okay, we're going to sort of look at the fibers. We're only going to sort of fix a single element of the computable structure and say, okay, let's just look at the fiber in this structure and say, how complicated can it be in this fiber? Okay, so there are a couple sort of easy examples of relationships between these things, between these different pieces. So the first one is that if I'm looking at all of these tuples where all I know is that the final coordinate is some integer, so it's not infinite, and it's not 0. I can computably enumerate this from just knowing the definable closure. And the way you do this is roughly the following. So I have some formula, Pxy, and I want to know whether or not there's, say, 7 elements. So I say, find a formula P7 of x, y1, y2, let's say 3. And I basically say this is equivalent to big or phi of x, y1, yi. So what I'm saying is I'm basically saying, well, either this formula of y1 holds, or the formula of y2 or y3 holds. So I then now search for a tuple of 3 elements that make this true. And I ask, removing one of those elements, is this formula in the definable closure? So if it is, that's saying that with only 2 of the elements, there's only one more possible realization. And so in this way, I can actually determine whether or not any finite k, there's exactly that many k realizations in a computably enumerable way from just knowing whether there's one realization. When there's just one realization. Okay. The next connection is we can actually determine from knowing when there's just one realization when there are 0 realizations. And this one's a little bit trickier. But what you do is you basically say, okay, I have a formula phi, and I want to know whether or not there is exactly there are no realizations. So what I do is I consider the formula psi, which is x, y, z, where this is phi of xy or y equals to z. So now what I can do is I can say, well, let's choose B0 and B1, which are the same type. And if right, and so I can ask, is there a unique realization of is phi a B0 z in DCL? So if there is, that's saying there's a unique realization of this. And now it could be the case that there's unique realization of BXY, in which case, okay, that doesn't have to tell us anything. But if there's a unique realization of BXY, we can then ask about B1. And if B1 also has a unique realization, well, then, right, then that sort of tells us that it must be in this case here, in which case there has to be no realizations. It's a little bit hand wavy, but I want to move on to a lot more interesting stuff. Okay, and lastly, not surprisingly, I can sort of, there are computer reductions from knowing the ACL and the DCL and knowing all the closure relations. Knowing sort of the number of realizations of any formula. Sorry, and the way you do this is if you know that in the ACL, you just search until you find the exact number of realizations, and then you go from there. And then you sort of use the first one. Okay. The next one is we want to talk about the relationships between the large capital ACL and the lowercase ACL. And once again, this is we can show that the lowercase ACL for any computable collection of formulas is computably enumerable, or sigma 1, 0, 1 over the capital ACL. So I know for any one formula, when there's only a finite many realizations, I can, in a CE way, determine whether or not a tuple is in the algebraic closure. And the way I do this is I basically say, well, being in the algebraic closure means there's some finite sequence of tuples, where at each stage, each tuple is in the one-step algebraic closure from the smaller tuples. And so if I can just find this collection, this sequence that terminates in my tuple B here, then I have to be in the algebraic closure. And so I sort of just keep looking for these tuples. Every time I find one, I throw in the end of it into the algebraic closure, and I sort of keep going. And this way I can sort of enumerate the algebraic closure, lowercase algebraic closure from the capital ACL. All right. And exact same argument works for the DCL. So I'm not going to dwell too much on this, but yes, the idea is for both of these, you know that lowercase ACL and DCL are sigma 1, 0, 1 from the uppercase ones. Okay. So now we want to actually consider just the quantifier-free formulas, because we're in a computable language, so when in doubt, quantifier-free formulas can actually get a computable handle on. And there are a couple sort of easy bounds that we sort of get. So first off, it's not hard to show that these are upper bounds, that for any computable specific model, ACL 0 is sigma 0, 2. You just write down what it means to say that there are finitely many realizations, and that gives you a sigma 0, 2 formula. And seeing as lowercase ACL is sigma 0, 1 over capital ACL, we know that lowercase ACL is also a sigma 0, 2 class. And now DCL is a little bit different in that we actually can get better than sigma 0, 2. You can actually get that DCL is the intersection of a sigma 0, 1 class and a pi 0, 1 class. And roughly speaking, the sigma 0, 1 class says for a formula, there is a realization of this formula. And so, because we're on quantifier-free formulas, testing any particular tuple is computable. So knowing there's a realization is sigma 0, 1. Likewise, the statement for any two realizations, they're equal. That's a pi 1 statement, pi 0, 1 statement. And so you get that being in DCL, you're in the intersection of these two. And so in particular, you are computable from 0 junction. Okay. Okay, so now the more interesting case is obviously the lower bounds. Like, are these bounds tight? And it turns out they are. So, and furthermore, at least in the quantifier-free case, we can find instances, realizations of this tightness that are monotheoretically nice. All right, so in particular, so this is the tightness of the ACL 0 bound. There is a computable structure such that the language has no relation, so it just has sorts. And for each ordinal alpha, the theory has exactly alpha plus 1 to the omega many models of size Alice sub alpha. So it's not technically totally categorical, or sorry, uncommonly categorical, but it's close. If you don't have this sort of blow up of continuum size models, at least below Alice sub omega. And furthermore, this set is one reducible to finite sets. So is very strongly a sigma 0 to complete set. All right. Now the proof is not super hard. It's basically look at all of the computable enumeration of all the things that terminate. And then what you do is you basically say, okay, because we have different many sorts, whenever I have a sort of element, element I put it in the sort E sub I in this enumeration. And so in this way, the model will be determined up to isomorphism by the sort of number of, so because the isomorphisms have to preserve the sorts, the model is basically going to be preserved by isomorphism, only to sort of care about whether or not a sort is finite or infinite. For any finite sort, you can pin down that completely in the first order theory, and an infinite sort, you can know it's infinite in the first order theory. So all you have is collection sorts which are finite and collection sorts that are infinite. And so in uncountable cardinals, all you can do is sort of say the cardinality of the infinite sorts to sort of pin down the model completely. And so that's how you get the number of models. But basically, knowing the ACL is exactly knowing when a sort is finite. Because I can ask, is this sort in the algebraic closure of the formula that says I'm in this sort? And if I know which sort is finite, I know precisely when there is a code which only has a finite number of outputs. And so in this way, ACL 0 is one equivalent to the set of finite sets. And therefore, this is sort of has maximum complex capital algebraic closure or one-step algebraic closure. Okay. Now, for definable closure, we have something similar, but the proof is significantly more in depth, so I'm not going to actually go through the details of it. So the language itself is very simple. It has one sort, a single binary relation. And structure is a countably saturated model of the theory of the structure. And you also have this property that for all ordinals, there are sort of alpha, there are sort of cardinality of alpha plus omega mini models of size Alice sub alpha, and they all have finite Morley rank. So if you know what Morley rank is, it's sort of great. If you don't, it's a rough measure of complexity of a model. And finite Morley rank is sort of saying that all definable sets are in some sense relatively simple. And what's more is like the saturated model has a computable array of subsets where basically all the models are appropriate collections of these subsets. But the set of things that connect, set of A where there's a unique thing connected to A is turn equivalent to zero jump. So the definable one-step definable closure is turn equivalent to zero jump, even though the model itself is incredibly nice. All right. As I said, this argument is much more intricate, so I'm not going to go into details on it. All right. So now, not surprisingly, we also have that the upper bounds on the lowercase ACL and DCL are tight, and that there's a computable set of quantifier-free formulas such that we can reduce finite sets to the algebraic closure. And as I said, given that we can reduce it to the capital algebraic closure and lowercase algebraic closure is, and the full algebraic closure is sigma 0, 1 over the one-step algebraic closure, not especially surprising. I'm also not going to go into details. Similarly, with definable closure, I can find something where the language is very simple and the collection of formulas we need. So remember, we're allowed to look at any arbitrary computable collection of formulas, look at the definable closure relative to those formulas. The formulas we need are only a single formula in order to sort of get the maximally complex definable closure relation. And we're able to also get that if there's a one reduction from the definable closure relation into finite sets. Okay. All right. So one thing we've done so far is we're giving upper bounds on the algebraic closure, on the one-step algebraic closure, one-step definable closure, and we've also shown there's a relationship between these things, which is not sort of surprising. We've shown that the full algebraic closure and the full definable closure are sigma 0, 1 over the actual algebraic, the one-step algebraic closure and definable closure. So if I happen to be in a structure where the one-step algebraic closure is really, really simple, the full algebraic closure cannot be too much more complex. It can only be sort of one existential quantifier more complex. And so the question is, can you go in the other direction? What happens if you know that the full algebraic closure is really simple? Can you deduce from that that the one-step algebraic closure also must be simple, or must be within something less than the full bound of the full upper bound of the one-step algebraic closures? And it turns out you can't. There are structures where the full algebraic closure and the full definable closure are trivial, but the one-step algebraic closure and the one-step definable closure are maximally complicated. All right, so in particular, there's two computable structures, C1 and C2. And they have the same language, which contained a single ternary function and a single unary function. So it's not a particular, it's a finite language, not particularly complicated. And they have both of the models agree on the unary relation. So it's only what's going on with the ternary relation where things are going to get interesting. And we have a single function formula, which is sort of definable in terms of the ternary relation. It has the property that in both of these structures, in the first structure, the algebraic closure and the definable closure are equal and they're trivial. They're basically, if your set does not intersect the unary relation, then you're everything. And if you do intersect the unary relation, then you're nothing. So all I need to do to test whether or not you're in the definable closure, the algebraic closure is, and I apologize, that should not say empty set, it should say A. There's nothing new in it. All I need to do is test whether or not the arguments intersect the unary relation. But I still have the sort of maximal complexity of the algebraic closure, that it is still a sigma 02 complete set, which is one reducible to finite sets. And the one-step definable closure is also Turing equivalent to zero jump. So knowing the full algebraic closure tells you nothing about the one-step algebraic closure. Okay, so now that we've done quantifier-free bounds, let's go to the full bounds. So we want to sort of now look at arbitrary sigma n formulas. And we want to sort of find some method of translating what we know about the quantifier-free formulas into the sigma n formulas. Well, the first thing we're going to do is we're going to do something called a computable moralization. And the idea is, so suppose so for those who don't know, moralization is the process of adding new relations to a theory, and thereby causing the theory to have quantifier elimination. So any theory whatsoever, any first order theory whatsoever can be moralized and be roughly turned into a pi2 theory, which has quantifier elimination. So what we want to do this in a way that that's computable. Specifically, when we create for each n, there is a language and a sigma 0 in constructive structure, such that if I have a computable structure I want to moralize. So I want to sort of add in new relations to the structure to sort of make everything quantifier free. And so roughly what I can do is I add in new relations, one for each formula. And for my structure, I basically say, this relation is equivalent to this formula. And so what you get is you get a new formula that is no longer computable. It's now sort of 0 to the n jump computable, because if I have a sigma n formula, that becomes a quantifier free formula. So it takes sigma, n jumps to sort of calculate it. But it's moralized, which means that every first order formula, which is a Boolean combination of sigma n formulas, is now equivalent to a quantifier free formula. Okay, so this is a good start because this tells us that we should be able to now use the relativization of our previous results to get some bounds. And once again, surprising, I'm sure no one will get exactly the bounds you pick. Is that if I'm looking at ACL CN, that's going to be sigma 0 n plus 2 sen. And likewise, DCL CN is going to be a delta 0 n plus 2 sen. And we get similar things for the full algebraic closure and the full definable closure. And the argument is exactly what we think it would be. Is I basically moralize, I take my structure, I moralize, so now I get a sigma 0 in structure. And now, but every formula is equivalent to a quantifier-free formula in a sort of computable way. And now I use the relativization over the previous result to get that the one-step ACL, one-step DCL, full ACL, full DCL of this sort of new structure is sigma 0, 2 in the structure. But the structure is 0 and computable, so it's sigma 0, 2 in 0 to the n. Therefore, sigma 0 to the n plus 2. This is for the one-step ACL. The one-step DCL is exactly the same. And so we basically get that these bounds relativize exactly the way you think they would. Now, these are the upper bounds. The lower bounds are more complicated because, normalization is a very simple process. All I'm saying, I'm sort of just relabeling formulas by relations and saying, well, yes, it's the formula, but really, why not call it a relation that doesn't really hurt you any from a computability point of view? But undoing that, basically saying, okay, coming up with a structure and a collection of formulas where the structure is computable, but the formulas that witness the sort of sigma in algebraic closure are maximally complicated in a sigma 0 n plus 2 way for one-step algebraic closure, say, that is substantially more complicated. But I'm going to give a very brief description of how this works. So we define a directed in-chain to be exactly what we think it is. It's a sort with a relation where the sort in the relation is isomorphic to the natural numbers of the successive. Now, before I continue, I'm going to sort of say briefly why we want this. So, as everyone knows, or hopefully everyone in this room knows, the pi 0, 2 sets are exactly the limits of the computable sets. The pi 0, 3 sets are exactly the limits of computable sets, and all the way up. So what we want to do is we want to sort of be able to encode this limiting structure into our relation. So we'll be given, we're given a structure which is sigma 0 and computable, where the quantifier-free formulas are sigma n plus 2, have sigma n plus 2, say one-step algebraic closure. And we want to translate that into a computable structure, whereby there is a sigma 0 plus 2, n plus 2, one-step algebraic closure for sigma n formulas. And the way we do this is we say, okay, I start with my structure, and then I add in the natural numbers. And what I do is I take this sort of iterative limit, and I basically say, okay, I'm going to add in the relation which I'm taking the limit of, and then my original structure the original relations in my structure are now formulas which are express the fact that I am this limit. All right, so go through it in a little more detail. But that's the basic idea. So it's we have a language, we have a sort with the natural numbers, and we have some function. And the idea is we have this. And we have some function on basically natural numbers to the k. And it's described in such a way that we can sort of, this is the one-step thing. So this is just natural numbers cross our structure. And we can define, it's described in such a way that at some point, the value stabilizes. I'm looking down the natural numbers. And so what this means is the sort of sigma 0, 2 set we're starting with is now a limit of this function here, of this sort of function. And actually, I want to sort of see if I can get this better next. Right. And so that idea is sort of iterate that idea. So we say, okay, I wasn't repeating myself, but now there's a slide. Is I basically say, okay, I have my structure, I have my relation, which is really complicated, and I sort of look at it's a limit of this sort of, say it's in sigma 0 in relation. It's this limit of n minus 1 or sorry, n plus 2 in relation, the limit of n many iterative limits. So this means that there's something on my structure across into the, let's say, into the lowercase n. And I can then express in a sigma 0 n way, or Boolean combination sigma 0 n way, what it means to be the iterative limit of this process. And so I now have a computable structure where I no longer have the original relations I started with, but I have a formula which expresses the fact that I am the iterative limit of the relation I've got. So that formula exactly defines the definable set that was sigma 0 in computable. Okay. And so in this way, what I can do is I start from the lower bounds I got on the quantifier-free, generalize it to the sigma, the 0 in jump lower bounds, unbounded structure. Then I apply this iterative limit process to get new relations. And then in this new computable structure, the formulas of saying the limit are now exactly the original sort of relations I defined. And so they have their algebraic closure is exactly as computable as it was in the original structure. All right, so hopefully that's roughly clear. If it's not, please read the paper because it's talked about in more detail there. Particularly, we have the following theorem. So for each n, there is a single computable structure such that the one-step algebraic closure on Boolean combinations of sigma in formulas. So, n many for all that there exists that alternate is a sigma n plus 2 complete set. So it's not just sigma n plus 2, but it's actually a maximally complicated. Likewise, we have that there's a structure where the definable closure is maximally complicated. It's equivalent to the n plus 1 Turing graph. And from this sort of sigma 1, 0, 1 property of the full ACL over the one-step ACL, we get that there is a computable collection of first-order formulas, all quantifier rank at most n, such that the ACL, the full ACL with respect to those formulas is maximally complicated. It's sigma 0 n plus 2 complete set. And similarly for DCL, there's a computable collection of formulas where it's a sigma 0 n plus 2 complete set is the full DCL, full definable closure. Okay. Sorry, this proof sketch is exactly what I sort of just described. If you sort of take the relativized version that we had before, every relation now becomes a limit of a computable relation, throw away the original relation, and then the limiting values become expressible in a formula, and you're good to go. Okay. Thank you.